Diploma in Electrical Engineering. Switchgear and Protection System. NoteWise Academy. Let's start. Smiling face heart heart. Unit 5. Protection Scheme. 5.1. Application of IDMT relay for HV feeder protection. Ans. 1. Overcurrent protection. IDMT relays are primarily used for overcurrent protection on HV feeders to detect and isolate faults promptly. They are configured to trip the feeder circuit breaker when the current exceeds a preset threshold for a specific duration. The inverse time current characteristic of IDMT relays allows for faster tripping for higher fault currents, offering better protection against severe faults such as short circuits. 2. Selective coordination. IDMT relays can be coordinated with other protective devices along the feeder, such as downstream IDMT relays, fuses, or overcurrent relays at substations. By adjusting the pickup current and time delay settings, engineers ensure that only the nearest protective device operates for a fault, minimizing the impact on the rest of the system. 3. Fault discrimination. IDMT relays provide discrimination between various fault types based on the magnitude and duration of the fault current. The relay can differentiate between temporary overloads and genuine fault conditions, allowing for selective tripping and minimizing unnecessary interruptions to feeder operation. 4. Backup protection. IDMT relays serve as backup protection for other types of protective devices, such as distance or differential relays. In case of failure or misoperation of primary protection, the IDMT relay detects the fault and trips the circuit breaker to isolate the faulted section until primary protection is restored. 5. Fault location and monitoring. IDMT relays can provide valuable data for fault location and system monitoring. By recording fault characteristics such as magnitude, duration, and location, IDMT relays help engineers analyze system performance, identify recurring issues, and optimize maintenance schedules. 6. Remote monitoring and control. Modern IDMT relays are equipped with communication capabilities for remote monitoring, control, and configuration. Integration with supervisory control and data acquisition (SCADA) systems or substation automation schemes enables real-time monitoring of feeder status, alarms, and events, enhancing overall system management and reliability. In summary, IDMT relays play a crucial role in HV feeder protection by providing fast and selective overcurrent protection, facilitating coordination with other protective devices, and offering valuable data for fault analysis and system monitoring. Their versatile features make them essential components for ensuring the reliability and safety of HV feeder operations in electrical power systems. 5.1.1. Time-graded and current-graded protection. Answer. Time-graded and current-graded protection are two common approaches used in power system protection to achieve selective coordination and ensure that protective devices operate in a coordinated manner to isolate faults while minimizing disruption to the rest of the system. Here's an overview of each. Time-graded protection. 1. Principle. Time-graded protection involves coordinating protective devices based on their operating time characteristics. Protective devices closer to the fault are set to operate faster, while devices farther away are set to operate with a time delay. This ensures that the device closest to the fault operates first, isolating the fault quickly, while allowing downstream devices more time to clear the fault if the primary protection fails. 2. Application. In time-graded protection schemes, relays are typically set with incremental time delays as the distance from the power source increases. For example, in a radial feeder protection scheme, the relay nearest to the power source, usually at the substation, operates with the shortest time delay, while relays farther down the feeder have progressively longer time delays. 3. Advantages. Time-graded protection is relatively simple to implement and provides effective coordination between protective devices. It ensures that the protective device closest to the fault operates first, minimizing the impact on the rest of the system and reducing the risk of widespread outages. Current-graded protection. 1. Principle. Current-graded protection involves coordinating protective devices based on the magnitude of the fault current. Protective devices are set to operate at different current levels, with devices closer to the power source set to operate for higher fault currents and devices farther away set to operate for lower fault currents. 2. Application. In current-graded protection schemes, relays are typically set with incremental current settings as the distance from the power source increases. For example, in a radial feeder protection scheme, the relay nearest to the power source may be set to operate for high fault currents, while relays farther down the feeder are set to operate for lower fault currents. 3. Advantages. Current-graded protection provides selective coordination based on the magnitude of the fault current, ensuring that protective devices operate only for faults within their specified current range. It allows for better discrimination between different fault types and reduces the likelihood of unnecessary tripping for transient or low-magnitude faults. Comparison. Time-graded protection primarily focuses on coordinating protective devices based on their operating time characteristics, while current-graded protection focuses on coordinating devices based on the magnitude of the fault current. Both approaches aim to achieve selective coordination and minimize disruption to the power system, but they employ different principles and settings to achieve this goal. In practice, a combination of time-graded and current-graded protection may be used to provide comprehensive and effective protection for power system components, depending on the specific requirements and characteristics of the system. 5.2. Earth Fault Detection Schemes. Answer. Earth fault detection schemes are essential for identifying and isolating earth faults in electrical power systems. Earth faults, also known as ground faults, occur when one or more conductors unintentionally make contact with the earth or a grounded surface. These faults can result in hazardous conditions, equipment damage, and system outages if not detected and cleared promptly. Here are some common earth fault detection schemes used in power systems. 1. Residual current detection. Residual current detection is a fundamental method for earth fault detection in both low and high voltage systems. It relies on the principle that in a balanced three-phase system, the vector sum of the phase currents is zero. Any deviation from this balance indicates the presence of a fault to earth. Residual current detectors measure the residual current flowing in the system and trip the circuit breaker if it exceeds a preset threshold, indicating an earth fault. 2. Earth fault relay. Earth fault relays are specialized protective relays designed to detect earth faults in power systems. They monitor the current flowing through the system's neutral point or through a dedicated current transformer, CT, on the earth connection. If the current exceeds a preset threshold, indicating an earth fault, the relay initiates a trip signal to disconnect the faulty circuit from the power system. 3. Core Balance Current Transformer, CBCT. CBCTs are specifically designed CTs used for earth fault detection in medium and high voltage systems. They consist of a toroidal core with a secondary winding through which the residual current flows. CBCTs provide a reliable and accurate means of measuring residual currents for earth fault detection. 4. High impedance differential protection. High impedance differential protection schemes are commonly used in grounded systems to detect earth faults. They rely on sensitive current transformers to measure the current entering and leaving the protected zone. If there is a significant imbalance between the currents, indicating an earth fault, the differential relay operates to trip the circuit breaker. 5. Impedance-based fault detection. Impedance-based fault detection schemes use the principle of measuring the impedance between the system conductors and earth. An earth fault causes a change in the impedance between the system and earth, which can be detected using impedance relays or other specialized devices. 6. Transient-based fault detection. Transient-based fault detection methods analyze the transient signals generated by earth faults, such as voltage or current surges. These methods rely on specialized algorithms or signal processing techniques to distinguish between fault and non-fault conditions and initiate appropriate protective actions. Overall, earth fault detection schemes are crucial for ensuring the safety, reliability, and efficiency of electrical power systems by promptly identifying and isolating earth faults before they cause damage or disruptions. The choice of detection scheme depends on factors such as the system voltage level, configuration, and operational requirements. 5.2.1. Residual CT connection. Answer. A residual current transformer, RCT, also known as a zero-sequence current transformer or a core balance current transformer, CBCT, is used to detect residual currents in a power system. Residual currents are the result of imbalances in the phase currents, such as those caused by earth faults or unbalanced loads. The RCT measures the vector sum of the phase currents and provides an output proportional to the residual current. The connection of a residual current transformer depends on the specific application and the protection scheme being used. However, there are two common configurations for connecting an RCT. 1. Zero-sequence connection. In this configuration, the RCT is connected in the neutral conductor of the power system. The primary winding of the RCT is connected in series with the neutral conductor, and the secondary winding is connected to the earth fault relay or protective device. This configuration allows the RCT to measure the residual current flowing in the neutral conductor, which is proportional to the imbalance in the phase currents. 2. Core Balance Current Transformer, CBCT, connection. A CBCT is a type of RCT specifically designed for earth fault detection. In this configuration, the CBCT is installed around all the phase conductors and the neutral conductor of the power system. The primary winding of the CBCT is connected in series with all the phase conductors, while the secondary winding is connected to the earth fault relay or protective device. By measuring the vector sum of the currents in the phase conductors, the CBCT provides an output proportional to the residual current, which is indicative of earth faults. The choice between a zero-sequence connection and a CBCT connection depends on factors such as the system configuration, the presence of a neutral conductor, and the specific requirements of the protection scheme. Both configurations are effective for detecting and protecting against earth faults in electrical power systems. 5.2.2. Core balance. Answer. Core balance, often referred to in the context of electrical systems and protection schemes, typically pertains to core balance current transformers, CBCTs. These specialized transformers are used to detect residual currents, particularly in three-phase systems, where the vector sum of the phase currents should ideally be zero under balanced conditions. Core balance transformers consist of a toroidal core with a secondary winding through which the residual current flows. Here's how core balance current transformers work. 1. Detection principle. Core balance current transformers operate based on the principle of detecting the residual current in a three-phase system. Under normal balanced conditions, where there are no faults or imbalances, the vector sum of the phase currents is zero, resulting in no residual current flowing through the core balance transformer. 2. Operation during faults. When an earth fault or other fault occurs in the system, causing an imbalance in the phase currents, a residual current is induced in the secondary winding of the core balance current transformer. This residual current is proportional to the imbalance and can be detected by the protective relay or monitoring system connected to the secondary winding. 3. Connection and installation. Core balance current transformers are typically installed around all the phase conductors and the neutral conductor of the power system. The primary winding of the core balance transformer is connected in series with all the phase conductors, while the secondary winding is connected to the earth fault relay or protective device. 4. Application. Core balance current transformers are commonly used for earth fault detection and protection in electrical power systems. They provide a reliable and accurate means of measuring residual currents, which are indicative of earth faults or other system abnormalities. Core balance transformers are particularly effective in situations where conventional protection schemes based on phase overcurrent or voltage cannot adequately detect earth faults. Overall, core balance current transformers play a crucial role in ensuring the safety, reliability, and efficiency of electrical power systems by accurately detecting residual currents and facilitating timely protective actions in the event of faults or system abnormalities. 5.2.3. Earth lead. Answer. In electrical systems, an earth lead typically refers to a conductor or cable that connects electrical equipment or components to the earth or ground. Here's an overview of the earth lead and its significance in electrical installations. 1. Purpose. The primary purpose of an earth lead is to provide a path for fault currents to safely dissipate into the ground, thereby reducing the risk of electric shock, equipment damage, and fire hazards. Earth leads are essential for ensuring proper grounding and earthing of electrical systems, which is crucial for safety and compliance with electrical codes and regulations. 2. Connection. An earth lead is typically connected to the grounding electrode system of a building or facility, which may include ground rods, grounding plates, or other grounding electrodes installed in the earth. The other end of the earth lead is connected to the metal chassis or enclosure of the electrical equipment or to the grounding terminal provided by the manufacturer. 3. Materials and construction. Earth leads are usually made of copper or aluminum conductors, which offer low resistance and high conductivity for efficient fault current dissipation. The conductor may be insulated or bare, depending on the application and environmental conditions. Earth leads may be installed as individual cables or as part of larger wiring systems, such as power distribution cables or equipment grounding conductors. 4. Significance. Proper grounding and earthing, facilitated by earth leads, are essential for protecting personnel, equipment, and property from the effects of electrical faults, lightning strikes, and transient overvoltages. Earth leads help to maintain the electrical system at a safe and stable potential with respect to the earth, preventing dangerous voltage gradients and minimizing the risk of electric shock or electrocution. In industrial and commercial facilities, Earth leads are a critical component of the overall electrical safety system, along with equipment grounding, bonding, and insulation coordination measures. 5. Testing and maintenance. Earth leads should be regularly inspected, tested, and maintained to ensure their integrity and effectiveness. Testing methods such as earth resistance testing and continuity testing can be used to verify the quality and functionality of earth leads and grounding systems. Any damage, corrosion, or deterioration of earth leads should be promptly repaired or replaced to maintain the safety and reliability of the electrical installation. Overall, earth leads are vital components of electrical systems, providing a crucial link between electrical equipment and the earth, and contributing to the safe and reliable operation of electrical installations. 5.3. Application of directional relay in loop feeders. Answer. Directional relays play a crucial role in loop feeders, which are common configurations in electrical power systems where power can be fed from multiple directions. Here's how directional relays are applied in loop feeders. 1. Protection coordination. In loop feeders, power can flow in multiple directions, making it essential to coordinate protection schemes to ensure that faults are isolated quickly and selectively. Directional relays are used to determine the direction of fault currents and coordinate the operation of protective devices such as circuit breakers or sectionalizers. By selectively tripping the appropriate protective devices based on the direction of fault currents, directional relays help minimize the impact of faults on the rest of the system and maintain continuity of supply to unaffected sections. 2. Fault discrimination. Directional relays help discriminate between faults occurring upstream and downstream of the relay location in loop feeders. By setting directional elements to operate only for faults occurring in specific directions, directional relays ensure that protective devices respond appropriately to faults without unnecessary tripping for faults in other directions. 3. Selective tripping. Directional relays enable selective tripping of circuit breakers or other protective devices based on the direction of fault currents. For example, in a radial feeder connected to a loop feeder at both ends, directional relays installed at the interface points can be set to trip only the circuit breaker closest to the fault, isolating the faulted section while maintaining supply to the rest of the loop. 4. Load transfer and restoration. In loop feeders, directional relays facilitate load transfer and restoration operations by ensuring that protective devices respond appropriately to changes in the feeder configuration. During normal operation or system reconfiguration, directional relays help maintain load balance and prevent unnecessary tripping or overloading of protective devices. 5. Fault location. Directional relays can also assist in fault location and diagnosis by providing information on the direction of fault currents. By analyzing the operation of directional relays at different locations along the loop feeder, engineers can determine the approximate location of faults and plan maintenance or repair activities accordingly. Overall, directional relays are essential components of protection schemes for loop feeders, enabling selective and coordinated operation of protective devices to maintain system reliability, minimize downtime, and ensure the safety of personnel and equipment. Their ability to discriminate between fault directions and coordinate protection actions is crucial for efficient and effective operation of loop feeders in electrical power systems. 5.4. Basic principle of distance protection and protecting zone. Answer. Distance protection, also known as impedance protection, is a widely used technique in power system protection schemes. Its basic principle relies on measuring the impedance of the power system to determine the location of a fault. Here's an overview of the basic principle of distance protection and the concept of protecting zones. 1. Basic principle of distance protection. Distance protection operates on the principle that the impedance of a power system changes significantly during a fault condition. During normal operation, the impedance between 2 points in the power system remains relatively constant. However, when a fault occurs, such as a short circuit, the impedance between these points decreases significantly due to the lower resistance path provided by the fault. Distance relays are designed to measure the impedance between the relay location and the fault point. By comparing this impedance to preset thresholds, the relay can determine whether a fault has occurred and, if so, estimate the distance to the fault point. 2. Protecting zones. Protecting zones are predefined areas of the power system that are assigned to specific distance relays for protection. Each distance relay is responsible for protecting a particular zone or section of the power system, typically defined by its distance from the relay location. The protecting zone of a distance relay is determined based on its reach, which is the maximum distance from the relay location to the protected section of the power system that the relay can cover. Multiple distance relays may be installed at different locations in the power system to provide overlapping protection coverage and ensure comprehensive coverage of the entire network. 3. Operation. When a fault occurs within its protecting zone, a distance relay detects the change in impedance and operates to trip the circuit breaker or isolate the faulted section of the power system. The relay operates based on preset impedance characteristics, which define the relationship between the impedance measured by the relay and the fault distance. Distance relays are typically designed with characteristic curves, such as MHO or quadrilateral characteristics, which provide different levels of sensitivity and selectivity for different fault conditions and fault locations. 4. Coordination and settings. Proper coordination and settings of distance relays are essential to ensure reliable and selective operation of the protection scheme. Coordination involves setting the reach and operating characteristics of distance relays to prevent unnecessary tripping and ensure that each section of the power system is adequately protected. Engineers must consider factors such as system topology, fault conditions, and relay settings when designing and implementing distance protection schemes to achieve optimal performance and reliability. In summary, distance protection operates by measuring the impedance of the power system to detect faults and determine their location. Protecting zones are assigned to specific distance relays to ensure comprehensive coverage and selective operation of the protection scheme. Proper coordination and settings are crucial for the reliable and effective operation of distance protection in electrical power systems. 5.5. Differential protection schemes for transformers, generators, and motors. Answer. Differential protection schemes are commonly used to provide fast and selective protection for transformers, generators, and motors, which are critical components in electrical power systems. Here's how differential protection works for each of these devices. 1. Transformers. Differential protection for transformers operates on the principle of comparing the currents entering and leaving the transformer windings. Current transformers, CTs, are installed on the primary and secondary windings of the transformer to measure the currents. The currents entering the transformer are compared to the currents leaving the transformer using a differential relay. Under normal operating conditions, where the currents entering and leaving the transformer are equal, the differential relay remains unoperated. However, if an internal fault, such as a turn-to-turn fault or a winding short circuit, occurs within the transformer, causing an imbalance in the currents, the differential relay operates to trip the circuit breaker and isolate the transformer from the system. 2. Generators. Differential protection for generators follows a similar principle to that of transformers. Current transformers, CTs, are installed on the generator stator windings to measure the currents. The currents entering and leaving the generator are compared using a differential relay. In normal conditions, where the currents are balanced, the differential relay remains unoperated. However, if an internal fault occurs within the generator, such as a phase-to-phase fault or a ground fault, causing an imbalance in the currents, the differential relay operates to trip the generator breaker and disconnect it from the system. 3. Motors. Differential protection for motors is typically applied to large motors where fast and sensitive protection is required. Similar to transformers and generators, current transformers, CTs, are installed on the motor windings to measure the currents. The currents entering and leaving the motor are compared using a differential relay. Under normal operating conditions, where the currents are balanced, the differential relay remains unoperated. However, if an internal fault occurs within the motor, such as a short circuit or a broken rotor bar, causing an imbalance in the currents, the differential relay operates to trip the motor starter and disconnect it from the system. In summary, differential protection schemes for transformers, generators, and motors rely on the comparison of currents entering and leaving the device to detect internal faults and initiate protective actions. These schemes provide fast and selective protection, helping to prevent damage to the equipment and maintain the stability and reliability of the electrical power system. 5.6. Buchholz's relay for transformer protection, alarm and tripping circuits. Answer. Buchholz relay is a specialized protective device used for the detection of internal faults in oil-immersed transformers. It operates based on the principle of detecting gas and oil flow variations within the transformer tank, which are indicative of developing faults. Buchholz relay is primarily used for providing alarm and tripping signals to initiate protective actions in case of incipient faults in the transformer. Here's how Buchholz relay functions in transformer protection. 1. Detection of faults. Buchholz relay is installed in the pipework between the transformer tank and its conservator tank, where the insulating oil circulates. The relay consists of a gas-filled chamber connected to the transformer tank. During normal operation, the gas remains in the upper part of the chamber, and the oil flows freely through the relay. If a fault occurs within the transformer, such as a winding short circuit, insulation breakdown, or partial discharge, it can lead to the generation of gases such as hydrogen and oil turbulence. The gas bubbles rise to the top of the relay chamber, displacing the oil and causing the oil level to drop. This change in oil flow and gas accumulation triggers the Buchholz relay to actuate. 2. Alarm circuit. Upon detecting abnormal oil flow or gas accumulation, the Buchholz relay initiates an alarm signal to alert the operator or monitoring system of a potential fault condition. The alarm signal can be used to activate visual or audible alarms, annunciator panels, or remote monitoring systems to notify personnel of the fault condition. 3. Tripping circuit. If the fault condition worsens or progresses, such as in the case of a severe internal fault or arcing, the Buchholz relay can actuate further to initiate a tripping signal. The tripping signal is sent to the circuit breaker or protective relay associated with the transformer, commanding it to trip and disconnect the transformer from the electrical system. Tripping of the transformer prevents further damage to the equipment, mitigates the risk of fire or explosion, and helps maintain the safety and reliability of the power system. Overall, Buchholz relay provides both alarm and tripping functions for transformer protection by detecting abnormal oil flow and gas accumulation resulting from internal faults. Its timely operation helps prevent catastrophic failures and ensures the safe and reliable operation of oil-immersed transformers in electrical power systems. Thanks for watching. Like, comment, subscribe, and share your friends' zone.